So as Gustav said, today we saw a lot of pristine band structures so far, but now when you want to do a calculation including some defects, it can become a little more difficult to interpret the band structure. So yesterday at the end of the tutorial, you calculated molybdenum deselenide in a pristine monolayer. And what I show here now is the monolayer with one defect atom. You might want to introduce a defect atom in order to locally change the electronic landscape so that you can, for example, bind an electron-hole pair to this defect and later excite a photon from it or relax it in some other way. When you want to do such a calculation with a defect, what you need to choose is a cell, in this case 3 by 3 pristine mono molybdenum disulfide cells, so that when you continue the lattice, the two defects are so far away that you achieve the concentration you want. Or if you want to have a kind of independent defect so far away that they don't interact anymore. In this case now we have one phosphorus atom in 27 other atoms. First of all, you do a relaxation of this phosphorus atom, and when you do the relaxation, this phosphorus atom gets sucked into the monolayer. Now what you would expect from such a defect system, because we have only very low concentration, is a band structure similar to the band structure of the pristine system with a little bit of perturbation. But when you actually do the band structure calculation in FLEUR, what you get is this kind of band structure. This doesn't look anything like the band structure you saw yesterday at the end of the workshop, and doesn't help you to kind of understand how this system differs to the pristine system. Also in photoemissions experiments like ARPAS, you wouldn't expect such a band structure which is folded back into the supercell, but you would rather expect the pristine band structure with a little bit of perturbation. So let's look at a simple example. Here we have a band structure of a quadratic band in some lattice with lattice constant A, but now plotted in a supercell of 2A. It's folded back into the double size supercell, which means half the size in reciprocal space, and you see this folding here. Now plotting this band structure for in the original reciprocal path, which is double the length of the 2A reciprocal cell, gives you this band structure. But where you want to go is to this band structure, the quadratic band, how it would be in the primitive cell. So what you need for this, you need to assign some kind of weights. And the reciprocal lattice constant in the 2A supercell would be this. Choosing one K point here and adding on one reciprocal lattice vectors would give you this K point. These two are symmetrically equivalent and have to share a weight. In the pristine case, this would be 1 and 0. And by assigning these weights, you can then go back to the original band structure. So how can we calculate these weights? Let's look at a square lattice with reciprocal lattice vectors G1 and G2, and one special K point in this reciprocal space. This K point is symmetrical equivalent to all the K points we can reach by adding on different reciprocal lattice vectors, so all of these ones. Now, looking at the same reciprocal lattice in a 2 by 2 supercell, meaning double the size in real space, half the size in reciprocal space, would give you this Brion zone. Now, here also the reciprocal lattice vectors are then half the size. Looking at the same K point in the supercell calculations and looking at all the symmetrically equivalent K points, you see all of these. You can now already see that one of the K points in the supercell has to contain kind of 4 times the information of one of the K points in the primitive reciprocal cell. Now, when looking at a plane wave basis with expansion coefficient C, you sum over all your reciprocal lattice vectors. So we could kind of think of how can we define some kind of weight. Looking at the norm of the vector, summing over all g would give you 1. But if we now restrict the sum over g's to the g's such that we only add up at the k points which we already would have had in the primitive reciprocal cell, so meaning this one, this one, this one, and this one, so only choosing combinations of g1 and large g2 so that we only end up at these ones, so summing over a subset of all the g vectors, we can get a weight somewhere between 0 and 1. So this is this condition written up here. This can be done for any k point. For example, if we would like to look at this k point here, we could only sum over these 4. Now for a plane wave basis, this is very easy. Because for a plane wave basis, the base is orthogonal, and we can just sum over the expansion coefficients. But as you learned yesterday from Gregor, our code is in the LAPW basis. And the LAPW basis consists of this spherical harmonic and radial basis functions in the muffin tins, and this plane waves in the interstitial, which are matched at the muffin tin boundary. And this basis is very useful because it already incorporates this 1 over r behavior of the Coulomb potential, but it's not orthogonal. And if you now try to restrict your sum and calculate the weights, you get this additional overlap matrix. So then the spectral weights, which we are looking for, don't look as simple as they did for plane waves, but have this additional term of the overlap matrix. Here now I show an example of silicon, calculated in the 2x2 supercell. And what you would get for the supercell band structure in the simple case would be all of these gray bands here, where you can already see this kind of folding into the supercell. If you would only have this band structure, it would be very hard to interpret, because you might think here's a maximum, here's a minimum, and silicon is a direct semiconductor. But now calculating these unfolding weights for the supercell calculation, you do get the blue bands, and you again restore the fact that it is an indirect semiconductor, and this might be interesting for any photoluminescence or photoabsorption experiments, where for optical transitions a direct band transition is much more probable, and therefore you want to know this fact. Coming back to the example at the beginning of my talk of molybdenum deselenide with a phosphorus defect, what you would get is this kind of band structure. And you can immediately see, when comparing it to the pristine band structure, that it looks like the pristine one, but with a little bit of perturbation. Now let's have a closer look at this. We can immediately identify this one band closely above the Fermi energy, which is due to the phosphorus having one less valence electron. And also we can observe the splitting at the Fermi energy due to this phosphorus atom. This we can also see at the density of states here. Wherever one of the atomic defects levels cross one of the energy levels of the pristine host material and the Hamiltonian interaction terms, we see this avoided crossings. And yeah, by this we can interpret the band structure a little more. And it is like you would see it in an ARPAS experiment, for example, that you only see a small perturbation to the pristine band structure. Now here I want to show you the effect of the size of the supercell you choose for your calculation. This is now molybdenum disulfide with a chromium defect, so not replacing the atom in the chalcogen layer, but replacing an atom in the metal layer. And on the left side you see the band structure with unfolding weights for a 3x3 supercell, so meaning 1 out of 27 atoms. On the right side you see it for a 5x5 supercell, so meaning 1 out of 75 atoms, so slightly above 1%. And you can very nicely see that here the effect of the defect is much stronger, and you can't really, or you can hardly guess what the pristine band structure had been, whereas for the larger supercell and the lower concentration with less interaction, you very nicely see this flat defect state with basically no dispersion like you would expect from an atomic level. Now, when you observe this defect state closer, you see this strong weight here, where the defect state is close to the conduction band state. And if you look at how we could understand this, I want to show you a simple two-band model. So here is always one defect band with basically no dispersion and one band with quadratic dispersion. And what is plotted here is in red how much weight the defect band has from the band in the quadratic interaction, and the quadratic band is just shown. And from left to right, the coupling between these two bands increases. From top to bottom, the defect level increases. So first, it's far below the minimum of the host state, then it's right at the minimum, then it's slightly above, then it's further above, and then it's far above. And now looking back at the band structure we saw here, we can look at what picture resembles it best. And then we can see that somehow here or here, the effect of this additional weight of the defect level, where it comes close to the host level, is resembled. And therefore we can understand this effect as kind of a resonance effect of the defect level with the host state. Now when you want to use this feature in FLEUR now, since we are looking at the practical application, you would set the band equals to false to true, like you did yesterday, and you can use this additional line. This additional line consists of 4 entries. One is whether you want to use the band unfolding feature or not. And the next 3 is just the size of the supercell. So for the calculation of 3 by 3 by 1 monolayer, 3, 3, and 1. FLEUR then calculates the path which would have been for the primitive cell, calculates the band structure along this primitive cell reciprocal space path, and then calculates the unfolding weights. And you do get a band output file which is called band _SC for supercell, like you get the band file yesterday. So I now showed you how you can go from such a supercell calculation, where you can't identify any of the original bands, to a band structure which resembles the original band structure. And by this, you can actually get band structures which look much closer to the ones you would expect in an ARPUS experiments or other experiments showing the band structure. Thank you very much.